Good morning and good afternoon. Welcome everyone to our plenary session from whichever time zone you are tuning in. Thank you very much for allocating this time. So we are so excited to have an amazing speaker that's about to give us an excellent talk in this plenary session that is hosted by Women in Radio Science. So I know that we are all looking forward to the talk and can't wait to listen to Dr. Midzor right away. I would like to, if I'm allowed, to use just maybe 1 minute to introduce you about Women in Radio Science. Women in Radio Science is a newest chapter of USNC-URSI. And it was initiated in 2018 with lots of support from Professor Urshilini, as well as USNC-URSI, and it started to come into being in 2019. And 2020, last year, we had our very first reception. And as of yesterday, we had our first business meeting, and this session is fully formed with all the officers on board. That's very exciting. It's a good year for us. And we will not have the chapter. We won't have Women in Radio Science chapter without our founding members. So I'd like to take a moment to acknowledge our founding members. Thank you very much for your service. And we look forward to have more members. And now I'd like to first thank the USNC chair for his support and tremendous work in helping us form our session. And I'd like to turn the time to Professor Sambiam Rangarajan for an opening remark. Thank you.
Okay, let me turn my video on. Anyway, I'm not sure it's not going on. Anyway, thank you, Rehan. Good day, ladies and gentlemen. I'm Sambiam Rangarajan, chair of the USNC-URSI. USNC-URSI is proud to have established the first ever Women in Radio Science chapter in URSI. They had their first business meeting yesterday, as Rehan mentioned, and are off to a great start with a plenary talk now and a reception tomorrow. Rehan Bakhtur, the chair of the WIRS chapter, and the founding members have been working hard to make it a very active chapter. Perhaps it may serve as a role model for all other national committees of URSI. I want to congratulate Rehan and other volunteers of WIRS for their accomplishments and wish them great success in their scientific and other endeavors to promote women in radio science. I welcome you all to this event on behalf of USNC-URSI. Thank you.
Thank you. So next, I cannot think of anyone better than Jean Quimby, who is the chair of this session. I'm co-chairing the session with her. I just could not think of anyone better than Jeannie to introduce our speaker. And Jeannie herself is an amazing leader and a great mentor who has been helping students and scientists in all level and the background. So next up, Jeannie. Thank you.
Thank you very much, Rehan. One of the wonderful things about working at NIST is not only the wonderful equipment that you get to use, but actually it's more important is the technical people. To say that I'm lucky to work with Melissa Midzor is very much of an understatement. Currently, she is the program manager for the National Advancement Spectrum for Communication Test and Network, also known as NASTN. This is a multi-agency group, which is hosted by NIST, which focuses on wireless communication spectrum sharing between commercial and federal systems. But prior to NIST, Dr. Midzor actually worked for the Navy for about 15 years, where she worked in electronic warfare, EW, and spectrum capability across many joint services. She served as the director for the EW Integrated Laboratories of NAVCWD and at the OSD Electronic Warfare or Countermeasure Office. She developed EW threat environments and tools to evaluate current and future RF technologies. You can always tell an old ex-government person by the number of acronyms that they put in their bio. She was appointed as the first senior scientist technical manager of the S&T EW at NAVAIR, and she received her PhD at some Podunk Little University known as Caltech in nanotechnology and imaging, and also holds a BA in physics and sociology from the the University of Colorado Boulder. Please, everyone, welcome with me with bright smiles, Melissa Midzor. Thank you.
All right, so let's welcome our speaker.
It helps if I take myself off mute. So, can everyone hear me now and see my screen?
Yes.
Thank you. So I want to thank Jeannie for asking me to speak today. While I really enjoy sharing my technical work, it's always a much more interesting challenge to provide an inspirational, my life as a career as a scientist with neat stories type of talk. So I'm hoping I do an adequate job of that today. My career has been marked by finding and following my passions, making a few huge career leaps, and an overabundance of planning. And these have led to some unique science and career opportunities, and I hope you find nuggets to take away from my examples. So the early years, I was obsessed with magnets ever since I was a child. I remember asking about magnets before I asked for a pony. So when I was about 8 years old, I had these magnets and I played with them constantly, and I always wanted to know more. And then in junior high and high school, I actually did science fair projects that were focused on magnetism and how magnetism affected conductive properties of metals. I realized I would need to go to college and get a PhD in physics or engineering to really understand electromagnetism. So off I went. And actually, I went to CU Boulder, and I started off in electrical engineering. And about year 2, I realized I was much more interested in the how, the why things worked, rather than just how they worked. So I actually switched over to a pure physics degree in my second year. And there I got to work on some really fascinating projects. I worked with the Stanford Linear Accelerator, aligning their shim magnets. And I also got to work on an antimatter gravity experiment and optimizing their magnetic trap. We were trying to measure whether or not antimatter fell at a different acceleration than regular matter. So little known theory off to the side. So again, always focusing on magnets. And then there was an event that changed my life and had a huge impact on my career. I got lost on my way to the grocery store. And while I was lost, I drove past the park and there were these people out there fighting with swords. And I parked the car and jumped out and asked who they were. And I've been with them ever since. It's a medieval sword fighting group called the SCA. And in that group, I learned really interesting skills. I learned how to organize, I learned how to managing. So not only do they do sword competitions, they do very large events. And I discovered that I had a passion for organizing and motivating people in this nonprofit organization. I learned really good skills on how do you motivate volunteers, how to communicate and convince others of ideas when, again, it's a volunteer organization, so you have to be very persuasive. And I also learned how to organize and manage and leverage the skill sets of a very diverse group of people. These people came from all different backgrounds and different skills and different interests. So how do you put teams together to achieve a goals? And so it was actually my hobby in medieval sword fighting that really honed a lot of my management and leadership skills. And also because of that interest, I realized that science wasn't enough for me. So I actually changed to a dual degree. I have both a degree in physics and sociology. Not only do I understand the understanding of how science works, I like to understand how groups of people work. So those early years really helped me try to understand how do you recognize your passions, and really trying to identify those and hone in on those. This will become more important later on. Then I headed off to grad school. I went to the University of Wisconsin to focus on plasma physics and its fascinating use of magnetic containment as a potential future energy source. However, about 1 year in, I realized it was interesting, but I wasn't truly passionate about it. And this was a hard decision. I've already passed all my quals. I've already passed all my first year requirements, and anyone who's gone through graduate school understands what an incredible investment of your time in your life is to get to that point. But I wasn't passionate about the work there. So that summer, I literally called up the West Coast, called Caltech and University of California. 2 weeks later, I packed my car and drove across the country. And I left it all behind and I ended up at Caltech. And there I got to focus on, again, magnets. I developed a new type of microscope called magnetic resonance force microscopy, but we applied it to ferromagnetic materials. IBM had started this research and they were looking at non-conductive materials. So they were looking for single spins and in isolators. We looked at magnetic materials. And this is a really fascinating technology where you're combining scanning technology and MRI to really kind of do MRI down at the atomic and micrometer levels. So it was really fun, a lot of interesting. It's a great thing to look into. And so after a lifetime of pursuing magnetism and understanding that universal mystery, I finished my PhD and realized I wasn't really looking forward to spending the rest of my life in a windowless lab anymore. So what should I do next? So this was my other big leap. I went to the career fair and I interviewed with Rockwell and Lockheed Martin and other science-based companies, but nothing was really grabbing me. And then I accidentally happened to wander past the McKinsey booth. And I was actually just waiting for my friend to go to lunch and was listening to them give their pitch. And this is a business consulting firm. And it was just fascinating, the examples that we're giving. And I realized this was a company that was looking at diverse new problems every few months. You got to learn a whole new business area every few months. You got to work with Fortune 100 companies and super smart people from all over the world. And I would get to use my people skills and really leverage my sociology degree, MISC experiments, and nonprofit group, which I really enjoyed working and organizing people. And so this just really sounded like fun. So after spending all of my life, 20 something odd years, focused on physics and magnetism, I left that to go off into the world of business management consulting. And there, going back to my passions, I really loved planning. So I got into strategic planning. I loved efficiency and making things run better. So I really focused a lot on operations for big things like chemical plants and mines. And got to work with really cool companies like Dow Chemical, even Nike. And one of my more fun projects was working for a window company. So windows, like actual glass that you look out of. That's actually a really fascinating industry. So working with these really well-known, respected companies and understanding what made them work well and how to make it better was incredibly informative. And there are 2 key nuggets that I got from the partners there, and I wanted to pass them on. One of them was to take stock every few years. So even if you love your job, every few years, sit down and look around and see if there's other jobs that are more interesting, more challenging, or something else that you might want to be spending your time on. So even if you love your job, just take stock every few years and see where you are and where you want to go next. And the other thing that they suggested, which I've been doing ever since, is 3 things. Pick 3 experiences at whatever company that you're at that you could only do that's unique to that company. So for McKinsey, because it was an international organization and it provided access to a lot of these interesting companies, my 3 things were visiting a chemical plant. I'm fascinated by large-scale engineering processes still. So I got to visit a really fascinating chemical plant down in Texas. I wanted to stay at the Waldorf Astoria because we're business consultants. They tend to put us up in nice hotels. And anyone who's seen movies, the Waldorf Astoria is a really famous, iconic hotel in New York that no one on anyone's normal salary could ever hope to afford to stay at. So I got to stay there. It was actually the smallest hotel room I've ever stayed in my life, but it was really neat. And I got to ride in a dump truck. There's a picture of me standing up there on the thing on the dump truck. That actually could carry 570 tons, if I remember. It was a specially outfitted truck from Caterpillar that was 20 tons higher than their normal largest truck. It was specifically made for that mine. So that was quite a trip riding around on that. on that dump truck. And so interesting enough, after I finished those 3 things, there was another event that changed. 9/11 hit. And I realized I wanted to do something a little bit more meaningful in my life than just work in Fortune 100 companies. I wanted to go back to something a little bit more technical, but I wanted to stay involved in strategy and management and leadership. I didn't want to go back into the lab. A friend of mine who worked for the F-14 for the Navy heard that I was looking for new opportunities. And so he brought me on board. And that started my next 15 years with the Department of Defense. So, and during these 15 years, it was really fascinating. I did everything from organizational change management to process improvement to electronic warfare, IEDs, and eventually created one of the largest EW test facilities in the country by connecting multiple labs and ranges. I do want to talk about some of those technical projects, but before I do that, I wanted to touch on some driving factors which ended up for a kind of a meandering career path through NavAir. I actually started in a group that did organizational change management. So we helped groups with strategic planning, cultural change, process improvement, and helped implement changes across different IPTs. I also helped the department develop their 5-year strategic plan. And as we wrapped up, I sat down, took stock, trying to figure out what I wanted to do next. And then I decided I was going to go be the lab lead for one of these aircrafts, for the EA-6B. And in the DoD, the labs are the furthest in the command chain from the leadership. So I wanted to take all those great strategies and goals that we had come up with at the leadership level and go all the way down to the bottom of the organization and see how you could deploy them. How can you deploy them bottom up? How can you get a team motivated about these things? So it was a excellent use of not just learning and using my technical side, but I got to use my organizational management and sociology and people background in trying to enact large cultural change in an organization from the bottom up. So I had an amazing team. They were quite successful, very pragmatic. They ended up achieving over 85% of their change goals, where the average for the other groups was only about 50. And then about 3 years in, that sit down, take stock, even though I enjoy what I'm doing, looking around to see if there's other opportunities that I think would be more interesting. And so I had several opportunities and several at NavAir, and I was having a hard time deciding between them. So I sat down and I had an individual development plan, which was only a 5-year plan, and I extended that to a 22-year plan. I'm quite obsessive about planning, if you ask any of my friends. So I came up with a 22-year management plan. I looked and said, what do I want to be doing when I'm 55 years old? I looked up people who had jobs of that type that I was interested in, and then I looked to see what their career paths were like and what skill sets that they had that enabled them to achieve that goal. So I developed a 22-year development plan, and then looked for opportunities, both jobs and rotational assignments and training that could help fill those goals and those skills along the way. I also want to mention, and you'll see it through this whole timeline, mentors. Mentors are vastly important, and not just technical mentors, but you also need non-technical mentors. They can really help you understand your goals, what you're passionate about, and where you might want to go next in your career and your long-term goals. So always have mentors and try to have 2 or 3. So after I came up with this plan, I took a right turn. And instead of trying to go up the chain, I actually went across, and we founded a new group called the Jewel Lab, which I'm going to talk a little bit about some of our highlights over the years next. And that was a great fun because I got to start a team from scratch, and I got to employ not just all my fun technical background, but I got to use my sociology and team building skills to try and really optimize this group along the way. Again, that was a lot of fun. And then I also did, as Jeannie mentioned, I got to do a rotation out at the Pentagon with the Office of the Secretary of Defense in their Electronic Warfare and Countermeasures Office. amazing group of people. If you ever get a chance to rotate around to different agencies, it's incredibly worthwhile. And then I came back and we started connecting all the labs and the ranges and ended up developing the electronic warfare integrated laboratory systems. But so over these 15 years, one of the things that I wanted to do was point out, you know, you need to plan, understand where you want to be in 5, 10, 20 years, and then look for opportunities to get you the skill sets you need to get there. And the second thing is enjoy what you do. Part of it is planning, but part of it is attitude. The saying of, you know, make lemonade out of lemons, all sorts of weird things would happen to us. But if you can look at, even if it's something that negative that happens, if you can look at it and say, okay, what does that change do? What opportunities does it bring? How can I leverage that to launch us in a new direction? You can have a lot of fun, even with massive changes that you weren't expecting. Oh, I also had the 3 things. So one was to visit all the NAVAIR bases. They had 5 military bases, but I ended up visiting over 50 military bases and research centers, including PACOM in Hawaii and CENTCOM out in Qatar, which is attached to Radio. So amazing experiences visiting all those different bases. I got to visit an aircraft carrier. Actually flew in and landed on the aircraft carrier, and it's not a fancy plane. It's basically what delivers the mail, but still, it was really impressive flying onto an aircraft carrier. And I got to fly in a simulator, and these are the simulators that the pilots fly in. So it's the most hopped up, expensive video game you're ever going to sit in. They're a lot of fun. So I do want to talk a little bit about some of the technical work we did, and with this being, you know, the radio group, I was going to focus specifically on some of the communication stuff that we did. So the Jewel Lab was the Joint EW Effects Laboratory. This was during the Afghan-Iraq wars, where there were a lot of IEDs, the Improvised Explosive Devices, roadside bombs, and so the military went out and just rapidly deployed a lot of jammers that went on the trucks to protect people, and then also at the entrances to the bases. However, if you just put out a lot of RF jamming, you tend to jam a lot of things. And so communications were never that great out in adversary areas, but again, they're having problems with communications and they blamed the jammers. And so our lab was launched to look at identifying and solving those compatibility problems between the different radios and the jammers. And first we had to develop a new method to determine interference on voice comms. There's actually no approved standardized method. I found out now that here I'm at NIST, we are developing those, but at the time there wasn't a standardized process on how did you measure whether or not you had good comms. And we were using real tactical aircraft radios. We had real jammers that we connected, you know, through RF cables and variable attenuators to simulate different levels of power of jamming. So we ended up creating getting audio equipment from Radio Shack, actually, to send synthesized voice messages from radio to radio, injecting different levels of power of jamming. And we had a voice recognition software on the other end. And then we calibrated the levels of interference, and we calibrated how well you could hear things by basically just using everyone in our lab as a guinea pig. And people had to sit down for hours listening to these recorded messages and translating them to see how well they heard them at different levels of jamming. So we used people to kind of understand what the automated system was doing, and then we could run these automated tests, because speed was of the essence. Every week we would meet with CENTCOM, and when you're looking into the eyes of the warfighters and people out there in the field, knowing that their lives are at stake, you go fast. So in less than about 2.5 months, we had built this entire test apparatus and system and had our first tests out. And some interesting things that came out of that with the communications. We actually showed that the interference was only actually due to jammers less than 30% of the time. Even though they get blamed for it all the time, the jammers were not the key source of the interference. And of course, the interference varied based on radio type and the jammer type. So the jammers had different types of modes that they used to jam the roadside bombs. And depending on their technique and depending on the type of radio, you would have different levels of power that you could use for before you had interference. We were also able to change some of the jamming techniques to minimize the interference. So there are certain hopping methods and certain cone techniques that we were able to employ to still effectively jam the roadside bombs, but allow communications. And we were able to reduce compatibility issues by over 90% over the course of a couple of years. So we were very proud of that. Just fun side notes, that things that we had to deal with. These are radios from tactical aircraft. They're used to flying at very high altitudes where it's cold. So we had to build special racks to cool all of our radios because we were running experiments for 14, sometimes 16 hours a day. So we had to cool everything at high altitude temperatures in order to get the equipment to run properly. Other interesting fun stories are just plugging things in. Military equipment doesn't come with a standard plug. So luckily we had a connector, the source of military connectors was actually in our hometown. And so we were frantically running over there at all hours of the day and night to build special cables so we could hook things up. So it was a very, it was fun, but it was also very impactful because every week we would be talking to the war fighters, giving them the information and knowing that it was helping them save lives. So the other things that we also looked at is we looked at interference, not just between comms, but UAVs. You had command and control and video between the UAV and the ground operators. So we were looking at solving interference issues with those. One of my favorite stories is over Christmas, we got word back that all the UAVs were flying south. So they were losing control of them and they couldn't understand why. And someone recognized that they were all flying south for some reason. It turns out that when they lose comms and control, the default setting for the UAV was to fly south if they didn't have a base programmed into it. So that's how we knew they were being jammed. And again, we brought it into the lab. We developed a whole new test apparatus to test UAVs and their CNC versus the jammers. And we were able to eliminate the jamming issues with the UAVs. And we actually, again, we literally got the call in January. We had everything up and running in 2 months. The other thing that we did, which from the radio wireless perspective, is that because we're in a lab, we're not outside, so we need to model propagation and the propagation techniques. And for low flying systems like UAVs, they don't really fly at high altitudes. They're fairly low enough, so ground bounce is an issue. And also cell phone towers, again, are close enough. They're not high enough to eliminate ground bounce issues. So we actually developed a modified version of the radar range equation, which we called a modified R to the fourth. We were able to use components of the R to the fourth elements in the equation and include it in our propagation model. And we were able to get incredibly accurate adherence to what we measured in the lab to outside. So we had less than a 10% difference between the lab measurements and outdoors. And that really helped a lot. Because it's much faster to run these tests in a controlled environment like the lab than to try and do them outside. Another fun thing was networked comms. They just started deploying networked radios. So these are self-healing systems. So if one radio is jammed, they can reroute the signal and the other radios can pick it up and continue translating the signal. So we had to develop a way to measure that, because with these self-healing systems, if I jam one, it didn't always react the same way because it was a networked system. And so we actually leveraged statistical analysis to help. And this was kind of new in the world of interference testing for the DoD. A lot of times they would go out and take 10 measurements and that was their data. And they assumed that the interference would be similar to what you measured that one time. But with these network systems, it changed all the time. Cell phones are the same way. And if you start playing around with a cell phone system, it does not react the same way every time. So we introduced statistical analysis to help provide them with the estimates and uncertainties for when they might see compatibility issues. And then of course we had to educate people on that. So those are just some key highlights from the Joule Lab. The other thing that we did is we developed what we called the EW arena. It was the many on many, because when you go out into the field, you just don't have radios. You have radios, you have UAVs, you have ground jammers, you have other sensors. And so we developed a hardware in the loop system that all of these things could see each other at the same time and interact. So real RF interacting with the real equipment in real time to understand how they worked. So that was our first EW arena, and this was just all RF cable, so connectorized testing. Then life got a little bit more interesting. IEDs, while still a problem, the fight was going back up to larger adversaries again. So again, we're looking at the surface-to-air missile radars, and how do you combat that? And again, you have multiple aircraft, you have multiple radars that are trying to track you. And again, the military was stuck in one-on-one testing. These are very complex radars and very complex waveforms. And so one-on-one was the way that they tested it. And so trying to connectorize this with RF cables was just not doable, because a radar might have anywhere between 5 and a dozen inputs. And the aircraft would have anywhere from 4 to 6 inputs. And so now you just have thousands of cables that you would have to connect up, and it's just not doable. So we came up with a new architecture called the digital EW arena, where we would digitize the signals and then use the digitized signals to pass it to all the other estimates. So instead of having thousands of cables, we were digitizing this. And this is a very challenging approach, because it needed to be flexible, because we wanted to be able to hook up different ships, different radars, different aircraft, different SAM systems. We wanted to hook up different systems so they could interact. We needed Doppler, phase, time delay. We needed clutter effects. We needed real RF interacting. And this all had to operate at tactical speed. So these things are moving really fast. Doppler is a huge issue. And we wanted to have connections so we can connect this to larger modeling and simulation and other interfaces. So we hooked up with MIT Lincoln Labs out there on the East Coast. We leveraged all the latest and greatest FPGA technology, and we built what we called Tournament. It would take the RF signals, it would digitize them, it would digitize them, put them in the FPGA where we could apply Doppler, phase, other propagation effects, and then we could spit it back out to the other systems. And it had to do this in less than microseconds down to femtoseconds. So the latest FPGAs were fast enough, had enough memory that they could take in that information, apply the modifications, and then shoot them back out again in a very fast manner. And in 2017, we were able to realize this ambition and did our first demonstration where we had a very complex radar, a SAM system, and we had 2 flying Durham jammers and a noise jammer going up against it. And this was really exciting because we had multiple jammers. You got to see how the multiple jammers interacted with each other. Durham jammers are very interesting, is that they'll take a signal, they'll modify it, and then spit it back out in an effort to jam. So if you have multiple of them in the same area, they're all listening to each other, taking in their signals, modifying them, sending them back, and then they modify it and send it back. So you get these really weird interactions from all these different systems constantly reacting to each other. And this was all a priori information. So just RF, things flying around. No system had any prior knowledge of where any other system was going. It was just as if they were out in the wild. And it worked beautifully. So we were very excited about that. So those are just some highlights from my time at NavAir. And then, so this is 15 years later, focusing on electronic warfare, testing, measurement. How do we get things to be compatible? across the different agencies. So I got to work with the Navy, the Air Force, the Army, and the Marines, everyone, because we all the equipment's out there together. So how do they work together? So after those 15 years, covering 5 very diverse and challenging opportunities, and I achieved my goal of connecting all the labs and the range, I again sat down to take my 3-year taking stock that I had mentioned before. And through a combination of personal reasons and just the decreasing happiness to pain level in my current job and the lure of Colorado, I decided to leap again. So that brought me out to NIST. Still following my passion in RF compatibility, so electromagnetism. I always go back to magnets. And it's fun being at NIST. So when I was at CU Boulder, NIST was that shiny place at the top of the hill. All there's really cool stuff going on and great scientists. So it's really an honor and it's just really neat to be working here at NIST. So what am I doing at NIST? A lot of you already know, considering the field that you're in, that there's a growing need for spectrum testing that's trusted. The federal government keeps auctioning off spectrum, and this presents a risk that there could be interference with existing assets and with science, weather science, all sorts of things. So again, it's just like before, it's spectrum compatibility, which I've been doing for the last 15 years, but instead of just the DoD now, it's the DoD, commercial, and NOAA, and NASA, and science, it's everyone. So same problem, just bigger. And so we really need approaches and technologies to help spectrum sharing and to measure their effectiveness and to understand when we have interference. So NASTN was founded in 2015. I joined NIST in 2018, so it already had a couple projects under its belt, but it's a multi-agency organization that includes NIST, NTIA, Department of Defense, NOAA, NASA, and NSF. It's hosted at NIST, that's where the core program office is, and it organizes the resources from all those different organizations, their subject matter experts, their testing facilities, to really solve spectrum sharing problems that no one agency can tackle itself. And we also provided trusted data. So we provide the modeling and the analysis to help support spectrum technologies, these new rollouts, spectrum sharing technologies. We provide a neutral source of data and measurements for spectrum policy and regulations. And we also provide, we can protect information, proprietary information, and then also classified information, because we work a lot with the DoD. And so we've done research in several areas. They're sharing in LTE bands. So how do they share within a same band? AWS3 is a key point. Also, what if it's adjacent? So they sold off frequency right next to your band. Whereas before it was quiet, now you have stuff radiating the band next to you. And as you know, RF always bleeds over a little bit. So are those out of band emissions actually causing issues? And then a third category is dynamic sharing. So there's new technologies out there like the CBRS system that is trying to dynamically share the spectrum. So instead of just saying you get frequency X and you get frequency Y, we're going to share the frequency, but we're going to share them at different times. So we're also looking at how those work. So a couple of highlights. One of the studies that we just finished was looking at aggregate emissions of AWS3. So they sold off the spectrum. The military is moving some of their systems out of there, but some of the systems are staying. So the commercial vendors have to limit the amount of systems they put out there so that their aggregate emissions, all their emissions together, fall below a certain level that would cause interference. So there's an agreed upon equation for interference and models that they run through to see whether or not they can deploy more. When they developed this model, it was very conservative. The DoD was very interested in protecting their system, so they erred on the side of caution, but they also had an ongoing program that was gathering the data to improve those models to get a better understanding of what was going on, in the hopes that they could reduce the requirements and allow more commercial wireless systems out there. So NASA was one of many teams supporting this. And we did 2 projects for them. One was factor screening, where we tried to really look at what were the key factors in a cellular network that influence the emissions that might cause interference. We actually characterized and modeled those emissions based on a subset of key factors. We did an analysis of assumptions. They did a lot of assumptions about these curves and the power control equation that is used to determine whether or not people get to be deployed. So we actually did an analysis on several of those key assumptions. And also characterized antenna patterns of the user equipment of the cell phones, which was actually quite different from what they were using in the models. And in the end, we had to create a whole new metrology to characterize these cumulative and complex interactions for cell phone emissions. It is not evident what's going on unless you really employ some advanced statistical analysis. So we ended up doing the largest factor screening experiment by NIST. We had over 28 factors, 32 settings, and what that comes out to is over 1,000 unique configurations, which we tested 4 times to eliminate variabilities due to weather and time. We validated all of the data, and it's important to remember that this was a commercial equipment. Commercial equipment is not intended for automation and frequent configuration changes. So we had over 1,000 unique configurations. We automated this all. The commercial equipment was not happy about that. So there was a significant effort not just to optimize the test matrix, but stabilizing this equipment in such a way that you didn't have hysteresis effects. And because we were able to take this data and validate on such a large scale, we were able to find key factors that couldn't have been found any other way than through statistical analysis. And then one of the main things is we found that the closed loop power control had a significantly smaller distribution in power than the open loop. You can see the graphic off to the side there, where if you're running your phone and your networks in open loop mode, it was a large variety of power that system could be operating over, but in closed loop, it could be much tighter. So that was unknown at the time. It was originally thought that open loop would be more power efficient. It turns out that closed loop was. We also found out that the measured power was not what was reported. All of the models relied on what the phones reported, and we found out that the measured power was not usually what was being reported. Luckily, it was always less than it, but we were able to model that and analyze it more completely. So a couple of key things that we were able to really improve the models as they're going forward. Just want to mention another couple projects. You can actually go to our website and learn more about these projects. We have all the results and the briefings and the reports, and also even the test plans are up on our website. We looked at LT impacts on GPS. So FCC auctioned off a bands that was right next to one of the GPS bands. That was suspended for a long time because there was a huge controversy about whether or not that was going to cause interference. And again, you had multiple measurements and multiple people saying completely different things. And so we were able to come in as a trusted neutral party to measure those effects. And this was one of the first projects by NIST, NTIA, and D. And we provided those independent test methods and data directly to the regulators and the stakeholder and commercial, so everyone got the data. Completely transparent about how we measured it. And recently, I think, FCC recently did approve Legato to go ahead and use that band. And in the report, NASA was cited 79 times for valid data used in helping them make their determination. And we're also very happy that they did note our recommendation for an improved metrology. So we also determined that there are ways that the measurement methods could be improved, and they did make note of that in the reports. We're also looking forward to the millimeter wave rollout. 24 and 28 gigahertz is coming out. Again, big controversy on whether or not this is going to impact, especially the weather instruments, the radiometer assets, especially at 23.8 gigahertz. So we're actually preparing to investigate that. We have a new 5G spectrum sharing testbed, which is at 28 gigahertz and expandable down to 24 gigahertz. It's real 5G commercial equipment. We have our test automation that we're developing for that. We have our experience in these stability tests, and also NIST has a group that does millimeter wave channel modeling. So we'll need this to extrapolate to effects in orbit. So we're preparing to get involved in this measurement. We're hoping that someone takes us up on it. So just wanted to quick summary. As I was going through my career, some of my big takeaways, besides some of the cool technology I got to play with, is really recognize and pursue your passions. What drives you? What gets you up in the morning? I haven't actually had to set an alarm clock in 20 years because I just get up every day because there's stuff I want to do. It's great. And don't be afraid to take the leap. Dare to make those changes while holding true to your passion. If you're really passionate about what you're doing, you're far more likely to be successful at it. So my career didn't always go up. Sometimes I went sideways. Sometimes I went down and then came back up again. But it was just, if I'm following my passion, good things will come. The power of planning. Know where you want to be, not just in a few years, 5 years, or 10 years. Figure out where you want to be long term. What type of jobs interest you, and find out what skills you need, and then find those positions, roles, or training that can get you those skills. And enjoy what you do, right? Not every change is a bad thing. Try and leverage it as an opportunity to try something different and new. And take stock every few years. Even if you're happy with what you're doing, look around, see if there's something that you would rather be doing instead. And above all, have fun.
Well, thank you very much, Dr. Melissa Midzor, for such an amazing presentation. And I have no doubt that not only we got to know amazing technology, but also we are quite inspired by the energy and the courage that you have translated through. So as per our agenda, next we are supposed to go to Q&A. But before that, I'd like to invite Jeannie Quimby, co-chair of the session, and Sambhya Rangarajan, chair of the USNC, to turn on your webcam and wave at the audience, because earlier you couldn't do so since I was sharing my screen. Okay, well, thank you very much. So now we will move on to question and answering session. We only have 3 minutes. So in case Jeannie and I couldn't see your question or give it to Dr. Midzor, good news, at 3:10, we have a drop-in discussion session where you will log in, and it's a similar Zoom chat. And the link is on Hua, so where you can log in and chat with Dr. Midzor and ask all the questions you want and get all the inspirations. So, okay, so we are open for questions. Jeannie and I will be looking for hands. So if you have a question, please use the reaction button at the bottom of your screen and raise hand, and we will call your name. At that moment, you are welcome to turn on your speaker and webcam for your questions. Thank you.
Mike, you have a question?
Sorry, Colin, I was fumbling with the controls, but Melissa, it was an excellent talk, not so much a question. I'm impressed with the career. It looks like you've done some amazing things. I think it's particularly fascinating that you've changed your path from time to time and look at where you are now. So it's a wonderful talk. I appreciate you letting us share in your journey.
Thanks.
I have a question, Rehan, but I can't, this is Zoya, but I can't turn on my video for some reason.
Maybe it's because someone has a share screen.
Well, there's a picture there. Melissa, thank you very much. This was a great talk. I'm Zoya Popovic. I'm at the University of Colorado Boulder. And I'm sad to hear that you were not an EE, but went over to physics. We'll forgive you. I was curious, actually, there were a lot of things I have questions for you about, but one is about the Joule program. What kind of techniques did you use to mitigate the interference? And I was curious about your statement that the jammers were not really the worst thing, or something like that. It was very fast, so I can't remember your exact words.
Yeah, actually, one of the biggest causes of interference was out of band emissions. A lot of people assume that if I had two jammers in the same frequency band, they would interfere with each other a lot. That actually wasn't the case. It was when you had a jammer at a different frequency band, the other jammer would then, if they're in the same frequency band, then they would just both jam.
Right.
But if they're in different bands, now they're trying to jam the roadside bomb, and they're trying to jam each other. So that actually caused more problems when you had things out of band.
That's super interesting. So you could get very broadband that way interference, and you don't know where it is. Yeah.
Yeah. We also discovered that the jammers needed a certain level of noise. If you sent them a very pristine signal, they would ignore it. We actually, when we did automated testing, we had to have the transmit signal of the threat device and a bunch of noise around it. So we had to do very broadband trigger signals because they were smart enough to say if it's a very pristine thing, it's probably not real.
That's super interesting. What a great problem.
Yeah, you needed dirty signals.
Yeah.
So, but yeah, we weren't quite sure what was causing the interference to the radios. There's just so much stuff out there, but at least we could take the heat off some of the jammers for a while.
And did you do any fancy beamforming, or was it all done at the kind of receive end in processing?
It's so we basically had to use whatever antennas the military was using. So we either had the real antennas or we emulated the antenna pattern of whatever system they were using. They didn't do a lot of beam forming. There was one jammer that did, it would jam forward and less backwards. So we, that was specifically.
Thank you. I don't want to hog the time. When did you say, Rehan, at 3:10?
Actually, yes. So this session ends right now, technically speaking. We will see how long we are allowed to stay here and chat, but otherwise at 3:10, there is a drop-in session with Melissa, and the link is on HUA. If you just go to HUA on the agenda, you will see it. So thank you again, all the audience, for being here, and we look forward to see you at the drop-in session as well as tomorrow's reception. Tomorrow we have a Women in Radio Science reception, and we look forward to seeing you tomorrow there. Thank you. Thank you, Melissa. Thank you, everyone.
Bye.
Bye.
Thank you, everyone. Great talk. Thank you.